Now in this segment of video, let us discuss IUPAC notation of a galvanic cell. As per the IUPAC norms, how to notate. So what is the representation of the galvanic cell in this form? Let us say. Always remember that in IUPAC form, always left side is always be anode, anodic of cell. Anodic cell we should write it in left side, and the right side is always be cathodic reaction. Left side is anodic reaction, right side is cathodic reaction, and vertical line, single vertical line, it represents electrode or the phase transition between the metal and its ionic solution. Okay, that we represent with a single vertical line, and the double vertical line, it represents a salt bridge. Simply, already I told you, just remember LOAN, loan, while writing the IUPAC notation. Left side is always we represent anodic reaction, right side always we represent cathodic reaction. Single vertical line indicates what? An electrode, and a double vertical line indicates what? Salt bridge. For example, if you take the galvanic cell reaction, zinc solid plus CuSO4 aqueous gives rise to zinc sulfate aqueous plus copper solid. This reaction, how we will represent? In two forms we can write. One is, what is the oxidation here? Zinc to zinc sulfate, na? So first you write zinc sulfate aqueous. So the single vertical line indicates what? Electrode. This is one electrode. Double vertical line, salt bridge. Next, copper sulfate aqueous, single vertical line, copper solid. So this is a representation, IUPAC representation of the above galvanic cell. Otherwise, as we know, sulfate ion is a spectator ion. No need of representing the spectator ions. You can also represent zinc solid, Zn plus 2 aqueous, double vertical line, Cu plus 2 aqueous, Cu solid. In this form also we can represent. In case if the electrodes are what? Gases. In case of gaseous reactions, platinum, hydrogen, HCl aqueous. So hydrogen is at P1 atmosphere and this is at P2 atmosphere. Platinum. So like this we can represent. This is one electrode and this is another two hydrogen electrodes. They are representing. They are at different electrodes, different pressures. This is what electrode concentration is. Electrode. Why? Because they differ in the pressures of the electrodes. So like this is a representation of the galvanic cells. And here one point you should remember while you are representing while you are writing the IUPAC notations, all solids, gases should be extreme terminals. That is why here zinc solid, copper solid. You should not write copper solid, single vertical and copper sulfate. Always the solid should be at terminals. That is the one logic. And always the ions should be nearer to the double vertical line. Means nearer to the salt bridge. Here ions, nearer to that. Okay. So this is a IUPAC representation of galvanic cell. And after that, so here whenever a metal is in contact with its metallic solution, aqueous solution of its metallic salt, okay, the potential that they generated, that potential we call it as what? Electrode potential. Electrode potential. So electrode potential is nothing but whenever a metal is in contact with its metallic solution, a metal is in contact with its metallic solution. So this is representing what? Single vertical line. Metal is in contact with its metallic solution. Whatever the potential generated, and that potential we call it as what? That potential we call it as what? Electrode potential, E. Okay, and this electrode potential generally we represent with E, and here reaction. So reaction can be a oxidation reaction or reduction reaction. For example, if it is oxidation reaction, how we will write E M M plus N. So indicates what? M becoming what? M plus N means oxidation. If it is a reduction reaction, how we will write E M plus N M. So here one point. So this is what? Oxidation potential SOP, and this is what? Reduction potential. So that point you should remember. This is what? Electrode potential. Then what is the difference between electrode potential and a standard electrode potential? Standard electrode potential. Standard electrode potential we represent with E naught. Whereas electrode potential E, that's it. Okay, it's E naught. So what is the standard electrode potential? The potential that was generated between the metal to its metallic solution at a standard condition. So what are the conditions we consider as the standard conditions? When the pressure is 1 atm, 1 atmosphere, and the concentration is 1, and the temperature is 298 kelvins. When you consider these conditions, then at these conditions, whatever the potential they generated, that potential we call it as what? Standard electrode potential. Remember that. Here temperature they won't mention, as well they didn't mention in the NCERT. They mentioned in pressure and concentration. Pressure should be 1 atmosphere and the concentration is unimolar concentration. At that conditions, whatever the potential that they generated, that potential we call it as standard electrode potential. As like electrode potential, here also we represent this with E naught. E naught indicates standard electrode potential, and here reaction. Okay, so oxidation if we consider E naught M plus N. So this indicates what? SOP, standard oxidation potential. So this is not standard OP, and this is RP. Here SOP, standard oxidation potential. This is oxidation potential only, and this is reduction potential only. Now this is what? SOP, standard. Why? Because this is a knot. Knot indicates what? Standard electrode potential and standard oxidation potential. Suppose if it is E naught M plus N becoming N, so what we can write? Standard reduction potential. And one point we should remember, as per the IUPAC notation, electrode potential, if they mention electrode potentials, so what they consider? Standard reduction potential, SRP values they consider as what? Electrode potentials, not oxidation potential. As per the IUPAC, SRP values they consider as what? Electrode potentials. Okay, so this is about the electrode potential, standard electrode potential. And one more thing, we cannot calculate the electrode potential of single half cell. For example, zinc to zinc sulfate. Suppose you take electrochemical cell, galvanic cell. Zinc to zinc sulfate is oxidation half cell. Copper sulfate to copper is reduction half cell. Can you calibrate the zinc sulfate electrode potential alone? No. One thing is, we cannot calculate the electrode potential of single half cell. Okay, always we can calculate the electrode potential of two half cells. By joining two half cells, only we can calculate the cell potential. Okay, so the electrode potential value of single half cell cannot measure. Okay, suppose if you wanted to calculate the electrode potential of a single half cell, how we can calculate? Simply you connect with some other known potential electrodes. That is what we call as what? Reference electrode. For example, zinc sulfate. You wanted to calculate SRP value of zinc sulfate. You wanted to calculate. Just connect this with hydrogen electrode. Why? Because hydrogen electrode is one of the reference electrode. Or a scalar electrode you can use. So the electrode potential of a single cell can measure by using some reference electrodes. Here, to calculate these electrode potentials, we are using some reference electrodes. What are the reference electrodes we are using? Reference electrodes means the electrodes whose potential is known to us and that we are using to measure the electrode potential of unknown. Okay, those electrodes we call as reference electrode. Generally, we use two reference electrodes. One is hydrogen electrode, that is what we call it as SHE. SHE stands for what? Standard hydrogen electrode. Also we call it as normal hydrogen electrode. So She or NHE, both are same. Standard hydrogen electrode. Then what is this standard hydrogen electrode? We will discuss that later. Next, one more thing is what? Saturated calomel electrode. Saturated, you don't think that is a standard calomel electrode. Saturated calomel electrode. In general, calomel electrodes are of three types. Okay, so here you write one thing. Calomel electrode you write CE, and these are of three types. Saturated calomel electrode, normal calomel electrode, deci-normal calomel electrode. Three types of calomel electrodes are there, but in general we use saturated calomel electrode. What is the difference between them? We will discuss, no doubt. Okay, first of all, standard hydrogen electrode if you take, what is this? Generally you take, okay, H plus solution. H plus means HCl solution. When the concentration of HCl is 1 molar, okay, and the pressure of hydrogen is 1 bar. Pressure of hydrogen is 1 bar. So when and we are using some inert electrodes. What are the inert electrodes? We use either platinum or palladium. Why? Because they will not react. That is why you just take the 1 molar HCl solution. Into that HCl solution you pass hydrogenic gas with a pressure of 1 atmosphere 1 bar, and to increase the surface area we are providing some inert electrodes. So by using this platinum or palladium, what happens? We are increasing the surface area so that the contaction between the gas and the solution will be more. Okay, so that is what. So when you provide that, okay, what is the voltage? So the voltage of standard hydrogen electrode is 0 volts. So what is that? 0 volts. So and this standard hydrogen electrode always we use it as anode to calculate the SRP of unknown. For example, zinc sulfate, you wanted to SRP of zinc sulfate. You take zinc sulfate as a cathode, hydrogen electrode as anode, calculate that. Why? Because SRP of hydrogen electrode is 0. So to measure the SRP of unknown electrode, standard hydrogen electrode is used as anode. Suppose if you wanted to calculate the SOP of unknown electrode, in that case you use hydrogen electrode as cathode and the unknown electrode as anode. So it depends upon the electrode potential values. Next, coming to the calomel electrode if you take. Calomel electrode is nothing but, so there was a mercury and the mercury is covered with mercury chloride. This is what we call it as mercurous chloride. That mercury is Hg2Cl2 and that Hg2Cl2 we call it as calomel normally. That is why we call this electrode as calomel, and that Hg2Cl2 is covered with KOH solution. Sorry, KCl solution. Okay, so first of all mercury. When mercury is covered with, this is what? This is Hg2Cl2 and this is KCl solution. Okay, so mercury chloride, this is what we call as calomel and that contact with KCl solution. This is actually under raw platinum white and it will act as a calomel electrode. Now the point you should remember, I told you already, three types are there: saturated, normal, deci-normal. What is the difference between them? These are we are classifying based upon the concentration of KCl solution. Suppose if in case of saturated calomel electrode, what is the normality of KCl solution? Molarity normality, if you take 3.5 normal KCl solution they use. Okay, saturated solution of KCl they use. In that saturation level, what is the normality? 3.5 normal. Okay, and in this saturated calomel electrode, what is the voltage? So it is not 0 volts. It is equal to 0.242 volts. 0.242 volts. Whereas the second one is what? Normal calomel electrode. Don't think that normal means not general. Normal means normality, one normality. So when one normal KCl solution was used, then that calomel electrode we called as normal calomel electrode. and whose voltage is little bit higher than that, that is 0.268 volts. In case of DC normal caliber electrode, DC means what? 0.1 normal KCl solution. If you use 0.1 normal KCl solution and its value was 0.338 volts, 0.338 volts. So like this we can calculate by decreasing normality. What happens? The voltage increases. In general, which caliber electrode we use? Saturated caliber electrode we use. So its voltage is 0.242. Okay, this is the reference. I think you know what is electrode potential, what is standard electrode potential, what are the reference electrodes we use. Okay, let us move to the next concept, that is what? EMF. So what is EMF and how to calculate the EMF of a cell, a galvanic cell intake? EMF stands for, it is nothing but electromotive force. Electromotive force. Yes, how to calculate it? EMF is nothing but it is the difference between electrode potentials of two half cells is called what? EMF. Simple logic. The difference between electrode potential of oxidation half cell and reduction half cell. Then the difference we call it as what? Electromotive force of the cell. So what is EMF stands for? It's nothing but the total voltage then that cell can generate. Simple logic. EMF of the cell means maximum how much voltage that cell can generate. That is what we call as EMF of the cell. Yes, how to calculate the voltage generated by the cell? There was a formula. There was three formulas are there. You know that left half cell is what? Oxidation half cell. Right side half cell is what? Reduction half cell. So if they given oxidation half cell SOP, standard oxidation potential of left side half cell, standard reduction potential of right side half cell if they given, anode to cathode different oxidation reduction half potentials they given, then simple logic, EMF is equal to SOP of anode. Why? Because at anode which process takes place? Oxidation process. That is the SOP of anode plus SRP of cathode. At cathode which process takes place? Reduction. So the SRP value of cathode. The sum of both we call it as EMF. Simple logic. And remember that one process, one logic is, if you know the SOP value, then SRP value is the same magnitude but with opposite sign. So that is a simple logic. There is SOP is equal to minus SRP or SRP is equal to minus SOP. Now based upon that, I am modifying the above formula. How I am writing? In the place of SOP of anode, what we can write? Minus SRP of anode you can write now. This is a minus term, this is a positive term. I am modifying this as what? SRP of cathode minus SRP of anode. So if both half cells SRP values they given, what is the formula? SRP of cathode minus SRP of anode. And the third one, if SOP values they given, now SOP of already we use. Now in the place of SRP of cathode, what we can write? Minus SRP SOP of cathode. So simple, one more thing is what? SOP of anode minus SOP of cathode. So by using these three formulas, you can easily calculate the EMF of the cell. One formula is SOP of anode plus SRP of cathode. Next one is SRP of cathode minus SRP of anode. Or else SOP of anode minus SOP of cathode. Simple. Three formulas. By using this, you can calculate. And after you calculate the EMF of the cell, whether the cell is spontaneous or non-spontaneous, how can you determine? Simple logic. If after you calculate the EMF of the cell, if EMF of the cell, E cell is 0, it is considered. If it is 0, that means the cell is at equilibria. The cell is at equilibria. Suppose if cell is at equilibria means there was no it will not generate the electricity, it will not consume the electricity. That's it. This is at equilibrium. Suppose if E cell is positive, then it will act as what? Electrochemical cell. Then that is a spontaneous process. It will take place. Okay, E cell is positive, then only spontaneous, and this is what? Reversible. Next one, if E cell is negative, then that process is what? It acts as electrolytic cell. Why? Because if E cell is negative, that is non-spontaneous. Non-spontaneous is by electrolytic cell. Clear? This is irreversible. So based upon the E values, we can decide. After you calculate the EMF of the cell, if EMF of the cell is 0, that is at equilibrium, positive spontaneous, negative non-spontaneous. Negative means it is acting as electrolytic cell, it is an irreversible. Whereas positive means spontaneous and reversible. That's it. Okay. Next, you may get the doubt. Sometimes what happens, two electrodes they give you, and they give you SRB values of both. So if SRB values they given, which electrode you should consider as anode, which will consider as a cathode? Generally the people will feel a difficulty here to differentiate that. One point you remember, whenever the two electrodes when they given, the electrode, suppose if SRB values they given, then let us consider, if SRB values they given, the electrode whose SRB value is more negative or least, okay, more negative, or else maximum, whose SRB value is higher, it always be act as a cathode. Just compare the two electrodes. The electrode whose SRB value is higher, that will act as what? Cathode. Why? Because SRB value is more means it is always tendency to reduction. At what electrode the reduction takes place? Cathode. That is why. So one point you remember, the electrode whose SRP value is high, whose SRP value is higher means less negative, more positive. Understood? So whose SRP value is higher act as what? It acts as cathode. Okay, and the electrode whose SRP value is lower, it will act as anode. Act as anode. So simply by using this, you can easily calculate what? You can identify which is anode and which is cathode. Once you calculate EMF of the cell, you can easily calculate. So this is about the electrode potential and how to calculate the EMF of the cell. Next, let us move to the next one. And generally, what are the factors on which the EMF of the cell depends? If you see that factors, the first factor is the EMF of the cell. Factors on which the EMF of cell depends. The first one is nature of substance. The second one is nature of solvent. Third one is temperature. The fourth one is concentration of ions. These are the main four factors on which the EMF of the cell depends. And the effect of concentration of the ion means how the EMF of the cell depends on the concentration of the ions. To explain that Nernst equation here. Clear? So let us in the next let us move to the Nernst equation. So before we move to the Nernst equation, let us finish the concept of electrochemical series here itself. Electrochemical series. Yes, what is electrochemical series? Electrochemical series is nothing but the arrangement of the metals in the increasing order of SRPs. In the increasing order of SRP or decreasing order of SOPs is called what? Electrochemical series. The arrangement of metals in increasing order of SRPs or decreasing order of SOPs called electrochemical series. So if you look at the electrochemical series, it will start with lithium. Okay, lithium plus ions to lithium. SRP values, that is by reduction, gaining of electrons. Lithium. Next, all 1A group elements, 2A group elements will come first one. So after lithium, cesium plus 2 cesium. Next, rubidium plus 2 rubidium. Next, potassium 2 potassium after 2A group elements. Barium plus 2 barium. Strontium plus 2 strontium. Ca plus 2 Ca. And then sodium plus 2 sodium. So all 1A group elements of 2A group elements metal ions are placed at the top of this series. At the top of the series. So check this. After 1A, potassium, calcium, sodium, magnesium. Okay, then aluminium, zinc, iron, nickel, tin, lead. Okay, after that hydrogen, copper, mercury, silver, gold. So like this, these all are having what negative values. Now, suppose if you take this one, it will be around minus 3.6, minus 3.4, minus 2.8, minus 2, minus 1.5, 1.8, 0, plus 1, plus 1.5, plus 2, plus like this. What happened by going down? What happened? The SRP values increasing. Okay. So one point you should remember. But from top to bottom. From top to bottom, what happened? The SRP values? SRP value increasing. From top to bottom, SRP value increasing. Next, from top to bottom, what happened? The reactivity. So SRP values increasing means reactivity decreases. Reactivity decreases. So these are the 2 points you remember. And what is the conclusion from the above electrochemical series? Conclusion is what is the use of this electrochemical series? So by using, just go through the NCERT book. So in the NCERT they have given a table so that you can understand. In that electrochemical series, all the metal ions which are present above in the hydrogen, all will act as what? All are what? Highly active, reactive metals. And those are present below in the series, below of hydrogen in the series, all are what? Less reactive metals. Okay, so this is the, once you go through the NCERT, you will get a clear idea. What is the conclusion from the electrochemical series? This is the very, very important. Conclusion. Conclusion first one. In the electrochemical series, the metal ion which is placed lower, lower means at the bottom. Okay, the metal ion which is placed bottom having high SRP value. Always the metal ion which is having high SRP value always will act as cathode. So the metal which is placed bottom will act as cathode, and the metal which is placed at the top will act as anode. That is the first conclusion. Just compare the two metals. In the electrochemical series, which is at the bottom will act as a cathode, which is at the top will act as anode. It's the first conclusion. The next one, if the metal placed at the bottom acts as a cathode, at cathode which process takes place? Reduction. So the metal which is placed at the bottom, undergoes which process? Reduction takes place. And the metal which is placed at the top undergoes oxidation. That is the second point you should remember. And the third one, when you compare the two metals, the metal which is present placed at the top will be more reactive, will be placed at the bottom will be less reactive. So the top metals are more reactive, and the bottom metals are less reactive. If they are asking the reactivity of the two metals, which is more reactive, always the metal which is present at the top. And because of the more reactivity, a top metal can displace bottom metal. Okay, the metal which is present at the top metals can displace bottom metals, but bottom metals cannot replace the top metals. That is one more point. And one more thing. Bottom metal placed at the bottom undergoes cathode. Na? Cathode means reduction. Na? The species which is undergoing reduction, what we call oxidizing agents. So the metals which is placed at the bottom will act as what? Strong oxidizing agents. Strong oxidizing agents. That means oxidizing agent power. The oxidizing agent power is directly proportional to SRP. Okay, oxidizing power is directly proportional to SRP. And the metal which is placed at the top will undergo oxidation. Okay, the undergoing oxidation means what we call reducing agents. So they act as what? Strong reducing agents. Strong reducing agents. That means what we can write? Reducing agent power is directly proportional to SOP. SOP are inversely proportional to SRP. So just remember these 5 conclusions so that we can easily identify which metal is acting as undergoing oxidation, which is undergoing reduction, which is acting as a strong oxidizing agent, which is acting as a strong reducing agent. Everything you can identify. Okay, once again, the metal placed at the bottom act as a cathode, top act as anode. Bottom metal undergo reduction, top metal undergo oxidation. Top metal is always more reactive than bottom metal. So the top metal can displace the bottom metal, and bottom metal undergoing reduction. So they act as what? Strong oxidizing agents. So oxidizing power is directly proportional to SRP value, and top metal is undergoing oxidation, and they oxidation. So the species which is undergoing oxidation we call it as reducing agent. So reducing agent power is directly proportional to SOP and inversely proportional to SRP. Okay, so this is about the conclusion. Now let us move to the Nernst equation.